Hi guys, in today's video gonna be going over hash tables. Hash tables are a powerful data structure that enables fast insertion, deletion, and retrieval of data. Hash tables are widely used in in programming. Right, so what's a hash table? Right, it's a data structure that maps keys to values using a hash function. Instead of searching iteratively or linearly, a hash table computes an index, making lookups extremely fast, usually O of one. It usually it changes up as you because there are different types of hashing methods, so it depends on the hashing method. But for the most part, it's O of one. And for those folks who have experience and background in Python, it is very, very similar to a dictionary where, a dictionary has a key and a value pair, right? So there's a couple types. The first type is direct hashing. Direct hashing, it overwrites data when a collision is found. Execution time is very fast since it does not involve a collision resolution technique. Data is lost when overridden and also should not be used when you want to resolve all data. Okay, so what does this mean really, right? So let's say you have um, this table right here. This table is just an array, and every index of the array is initialized to a value of -1, so we know if it's empty or not. And right, so let's say we want to store an array of numbers. What we do is we take the direct hashing function, which for the most part is usually n modulo 10, which is the size of the array, and then this gives us the index that we are going to store our n value in. So in this case, we are storing our n value at index 4, so we are overriding our -1, which indicates an empty space, and setting it to 4. So as you could see, you could kind of imagine where a problem in reserving data would occur, because let's say we have another number, for example 14, in our array. 14 modulo 10 is 4 again, so what would happen to the 4 is it will just be replaced by 14. So we have no recollection of that number 4 within our direct hash table. So let's continue. Okay, this example does it for us, right? It overwrites number 4 with 24. Again, this is very quick. This is a very solid method. But if we are trying to reserve data and we want to see exactly where what numbers we're storing in our hash table, we need to make sure we do not use this method. Same thing here. Here too. Modulo 10, 56. Okay, and this is the function. You see, you're just passing in an array. You're passing in an array. Again, we're running on line 14. We're running the actual hashing function, right? For the most part, it's x being the number that you're inputting, modulo the table size, and then again, you're just overriding every single time, regardless if there's a value or not already at that index, the value with x. Okay, this is a very, very important hashing function, hashing type. This will 100% be on the exam, guys, so make sure you guys pay attention to this. So this is the same idea as direct hashing. Very, very similar, right? At every index, you're going to store a value. But what was the problem we ran into originally? The problem was, hey, let's say you had multiple numbers that had the same output for the hashing function, right? The hashing function is what determines what index is gonna house that number, right? This separate chaining method, it gives us a solution. It gives us a way out of that collision, of that overriding, right? So each cell of the hash table points to a linked list. You see, this is why I always emphasize that, guys, like, linked lists are very, very important in data structures, everything stems from linked lists. Like if you understand how linked lists work, you will understand how a majority of the remaining data structures works. Okay. Record F records that have the same hash function value. Hash table never fills up because more elements can always be added to the chain. Again, the chain in this case is linked list. So earlier in the video, I said if a certain hash value keeps happening, it can cause the search time to become O of n. This is what I'm talking about. If you have numbers like 1, 11, 21, 31, 41, so on, eventually when you want to search for number 91, for example, you're going to have to get to index 1, and you're going to now have to iterate through the linked list, right? Using whatever linked list function you want to use. And you're going to have to iterate to the back of the linked list n times. You see what I'm saying? In a normal hashing, direct hashing, you obviously don't have to worry about the O of n stuff because everything gets overridden. Everything gets, there's collisions occurring. Again, so that there's always a downside to everything. But again, if you are focused on reserving all the data being inputted, definitely recommend to use separate chaining. Okay. So we're going to use the same numbers, right? So we still use the same hashing function of x module table size. 4 is null, so we can simply add index at the head of index 4. You see, this is the head now. And now we want to add 24, so we add to the back of the linked list, right? So just inserting at the back of the linked list. So you iterate. So you go to index 4, you iterate, right? If it's null, you replace it, right? It's super easy. You just set index 4 equal to new number, new node at with value number. If not, you use a temporary pointer, right? You iterate to the back, the very back of the linked list, and then you put the new node there. So on and so on, right? You see how it keeps getting added to the back of the linked list. This same idea, 56 module 10 is 6. It's null. We could just do a simple index table at index equals head or whatever equals new node with value 56. This is the code to it. Again, we're gonna initialize a normal linked list node. You're taking in a dynamic table. New node. If table at index is null, right? So if the head is null at that specific node, okay, just head is equal to temp. Very easy. Else, you iterate to the back of the linked list using a temporary pointer, the current, and then you just set current next equals temp. Okay, so that's this again, guys. The separate chaining is a very important topic, very important type. Definitely recommend that you really understand that type. Linear probing, it's a little different than a direct hashing, but it's the same idea. But this time collisions do not occur because you use this formula, right? You use the hash function, but instead of just automatically using the hash function on that index, you have to first check if it's empty or not. If it's empty, go ahead and just use the hash function on that specific position. If not, you're going to iterate and add 1 to the hash function. If that space is not available, you're going to add 1 to that. So, we're kind of using a for loop, and I being the thing that is being incremented. And, as soon as we get an empty spot, we can go ahead and grab that. Okay, so this is the hash function. This is the index, right? The I in the for loop. Again, we're still at the 0th, position. We are able to replace -1 with 4 because no collision or overriding occurs, so we're good to go. Now we're with 24. This is the hash function. This is the original iteration through the for loop. Obviously, 4 is already taken. So what we do is we go back to the beginning of the for loop, the top of the for loop, and we iterate. So we do I++, right? 1. Now our I is 1. 24 module 10, 4, same thing, plus 5 module 10, 5. Okay, guys, I forgot to mention that this module 10 is used to make sure that our indices are within bounds of the table. Because, if you have a maybe you get to like a spot in the for loop where you hit like the 10th I. If you do that, there's a very good chance that your index will fall out of range of the table size. That's why we have this extra module 10 to ensure that our indices fall in place. 134, same idea. We're gonna go one time in the iteration of the for loop. 4 is taken. We're gonna go another time. 5 is taken. We're gonna go one more time. Oh wait, 6 is not taken. So we go ahead and do that. The last thing is 56. Same idea. Hash function plus current I, which again starts off as 0. If it's taken, since it's taken already by 134, we do that. You see how it's kind of inefficient. In my opinion, again, like just going through it, I just definitely go for the separate chaining because it for sure can house all data needed, right? I would never take a chance of risking my data and losing the data if I have to make a compromise on the actual iteration time complexity. So we're making an index. This is going to be used here. This is the for loop I was mentioning earlier. Hey, could start at 0, and every time we hit an index that is not empty, we're just gonna go back to the top of the for loop and iterate plus plus. This is the hash function right here. This is the I. We are incrementing every single time an index is not empty. And this is the for loop. This is, hey, if it's empty, just go ahead and set that current index to X and break, because we no longer need to iterate. Quadratic probing, in my opinion, I don't understand why it entirely exists. It's very, very same idea. It's very similar idea to linear probing, but instead of just doing a simple plus I to the hash function, you're actually doing an I squared. Again, I don't entirely know why we do that. There will be less clustering in the hash table, but again, I don't know if that adds too much of a benefit when it comes to hashing. Quadratic probing is faster than linear probing in terms of searching and inserting. Okay. Same idea. Instead, you square, right? Again, it's empty, add it. Same idea, it's not empty, increment by I, add. So 5. Same idea. You increment since it's taken already. You increment since it's taken already. You increment, and it's good. Again, pay attention to the squared. It is always going to be quadratically squared, I guess, whatever. But the index increases every single time you hit a spot that's not empty. Same idea here. Obviously 6 was not taken since, again, we're using quadratic probing. So we can go ahead and take that. This is the same exact function as linear probing, but in this case, we are squaring I right here. Double hashing, very, very simple, right? So when a collision occurs, we use another function called hash 2x to look for an empty index. So what we're doing is hash 1x, so the same hash function we're using, x module 10, plus I times hash 2x module table size, where I is incremented by 1. So it's the same idea. We're always going to increment by 1 if that specific index is not empty. So this is our hash function, original function. This is our hash 2 function. Again, this x, no, let's use another term, p minus x minus parentheses, x modulo p. P can be any prime number. Again, for the most part, we'll probably give you a hash 2 function, if anything. And the modulo 10 to ensure that, hey, we are staying in bounds of the table size. Okay, now that we took that spot, right, let's go to the 24. What's the same thing is going to happen, right, as previous times. We notice that, hey, when we take the 0th value for I, and we try to plug it into the hash 1 function plus that whatever hash 2 function times I modulo 10, we get 4. And we notice that, hey, 4 is already taken. It's already filled with the value. And this double hashing ensures no collisions or no overriding of data. So what we're gonna do is, hey, in the for loop, right? Picture the for loop. We're gonna now jump to the next index. We are incrementing I by 1. Same exact function. And this is a mistake, by the way. This is supposed to be 24. Same exact function. But we are doing now 1 times hash 2 function. So you see how it gets all pushed all the way here. Same idea here, 134 hash 1 function plus 0 times hash 2. Again, 4 is already taken. Iterate until we get to the next available spot. Take it. 56, same idea, but there's no iteration needed since the 0th I value is already not occupied. Okay, this is the double hashing function. Very, very similar again to linear and quadratic. Okay, so guys, there's three methods that are very similar to each other, right? Linear, quadratic probing, and double hashing. All very similar. They all have the same idea. Hey, you're gonna use a for loop. Do whatever is needed in the for loop. If that math does not result in an empty index, you're just gonna go back to the top of the for loop and iterate to the next index and do the same math, right? In this case, the math is hash x plus I times hash 2 module table size. Again, if that doesn't cut it, that does not cut the needs for that specific iteration, you're gonna go back here and I plus plus. And also, just let you guys know, there is a standard library for maps, key and a map value. Key values used to store and identify the elements in the map. Map value stores the data that is associated with a specific key. There can be no duplicates keys in maps. The mapped values for key can be accessed using a bracket. And I definitely recommend, guys, that whenever you guys do a leak code question, you definitely look at the possibility of you using a map or a Python dictionary. I definitely recommend it because a lot of problems can be solved using a dictionary or a map. This is a function called contains duplicates. Given an array, integer array in size, return true if the array contains any duplicates and any false and false otherwise, right? So obviously 1 2 3 4 3 contains duplicates, so true. Contains duplicates 1 1 true. 1 2 3 4 5 does not. So the function use a standard library. If you iterate through the array, right? If the current index in the array already exists within the map, go ahead and just return true. Because again, our whole idea is we don't care how many duplicates there are. We only care if there's one duplicate. So as soon as we hit an index that is already stored within the actual map, just go ahead and return true. Else, right, if it's not true, set that index in the map as true, because again, the map is initialized as all false. But our task is to, hey, whenever we reach an index that is true, or an index that is contained within the map, within the array, we need to make sure that we contain the map. We we store the map's value at the specific index as true. So when we run through it one more time, we know, like, hey, again, we already have this index within our array. So if it appears as true within our map boolean or our boolean map, we know that it's a duplicate. So we return true and end it. If not, if we iterate through the whole array and we don't run into any issues with the if statement, we can return false. This is a very similar idea. An anagram is a word or phrase formed by rearranging letters of a different word, typically using all original letters. So you're going to initialize 2 character maps. Again, this is very obvious. This is just like more of a, like, hey, just to have it to maybe cut down some time. We add every index to the right. We map every key to the value in the in the maps, right? The key being I in this case, the index, and the value being the actual character. If if the original string does not match, if the array at the original string does not match the array at um the index at the original the second string, we go ahead and return false. Else we return true. And so this is all I have for hash maps. If you guys have any questions, please message me on Teams. Thank you.